For over a century, scientists have tried to measure the gravitational constant g, and yet, it remains the only fundamental constant that refuses to settle. Even with ever-improving precision, different laboratories since the year 2000 still report values that differ by 100 to over 300 parts per million, despite claiming internal uncertainties as low as 10 to 20 ppm. That's extraordinary when compared to other experimentally measured constants, like Avogadro number, the Bohr magneton, or the electron's magnetic moment, all known to astonishing precision, within a few hundredths of a part per million. So why does g behave differently? Why does gravity, the oldest known force, remain the least well measured? Could it be that we are missing a variable, something subtle but real, hidden inside the materials or the way we measure them? This question is the starting point for everything that follows. So if mass and distance aren't the whole story, what else could gravity depend on? Some physicists have proposed a radical possibility, that gravity isn't a fundamental force at all, but an emergent phenomenon, a result of changes in information and entropy. Dutch physicist Erik Verland proposed that entropy, essentially the degree of disorder or information complexity, might influence gravity. In his view, the more disordered a structure is, the higher its entropy, and the stronger the gravitational effect it could produce. This entropy-gravity theory has never been tested directly. That's what we want to do with our experiment-coded G6. Let's talk about the experiment itself, G6. At its core, G6 is designed to isolate a single variable, the internal entropy of a physical object. Here's how it works. We start with a sealed, solid container filled with high-purity graphite. We measure its gravitational pull using precision instruments, such as laser interferometers. Then, without opening the container or changing its position, we use ultrasound to crush the graphite inside, turning it into fine, disordered carbon powder. What stays the same? The total number of atoms. The container. Its shape. Its orientation. What changes? Only the internal structure, from ordered crystal lattice to chaotic powder. If entropy plays no role in gravity, the gravitational pull should stay exactly the same. But if entropy does influence gravity, even slightly, we expect to see a small, measurable increase in gravitational attraction after the material becomes disordered. That's the heart of G6, a minimalist, controlled experiment to see whether information structure matters. According to the current law of gravity, only two things matter: the mass of the object and its distance from the detector. In G6, we don't open the container. The mass stays the same. The measurement distance stays the same. By classical physics, the gravitational reading should therefore remain unchanged. However, entropy-based gravity hypotheses allow a small but measurable change after the graphite is crushed into disordered carbon powder. To keep the claim testable and transparent, we state our prediction as tiers informed by post-2000 evidence, including orientation-dependent anomalies about 30 to 60 ppm reported in 2009 to 2018 Huazhong University of Science and Technology G experiments. Classical baseline, no change. Conservative entropy effect, more than 30 ppm increase after disordering. Plausible range, 50 to 150 ppm, motivated by the 30-60 ppm orientation dependence observed without deliberately increasing entropy. G6 imposes a much larger entropy change than mere rotation. Stretch upper bound, may even over 300 ppm. HUST observed G differences of 30 to 60 ppm when the gravity source is turned around. This anomaly is an important motivation for designing the G6 experiment. G6 is designed to decisively distinguish between these outcomes by holding mass and geometry fixed while changing only internal entropy. Why a cube-shaped container? At first glance, the shape of the container might not seem important. But when you're looking for a signal as small as 30 parts per million, even minor asymmetries can matter. Most traditional G experiments use metal spheres as gravity resource. But here's the issue: spheres don't have a fixed orientation. It's hard to ensure the same region is always facing the detector. If one side of a sphere has more defects or entropy than the other, small rotations between measurements could change the gravitational reading. In fact, between 2009 and 2018, 3 generations of G experiments conducted by HUST consistently observed that the measured value of G depended on the orientation of the source masses. A stable, repeatable effect still not fully explained today. That's why G6 uses a cube. Cubes have flat surfaces, sharp edges, and clearly defined faces. We can mark one face and always place it in the same orientation. This ensures the structure's alignment is consistent across measurements, allowing us to isolate the variable we're actually testing: internal entropy. There's another reason too. A cube-shaped container can be densely filled with graphite much more easily than a sphere or cylinder. This matters because once the graphite is shattered by ultrasound, it expands. If the container had empty gaps to begin with, the carbon powder would spread into that space, shifting the overall center of mass. That would introduce unwanted variation in the gravitational reading. To avoid that, we want to start with a tightly packed container, and a cube is ideal for that. If one face of the cube is marked, how can you ensure the cube remains perfectly symmetrical? G6 doesn't require perfect symmetry, and that's one of its major strengths. Unlike traditional G experiments that demand extreme machining precision, G6 focuses solely on the change in gravitational pull between a high-entropy and low-entropy state, using the same object in the same orientation throughout. As long as the container always faces the detector in the same direction, any asymmetry, even from a slightly imperfect box, becomes a constant background. It cancels out in the before versus after comparison. So yes, you can mark the container with something as casual as a Shy Kitty sticker, and it still works. That's the elegance of G6. Simplicity, repeatability, and no need for ultra-expensive fabrication. Why compress first before sealing? Shape isn't the only concern. Inside the cube, we need the graphite to be packed as densely and uniformly as possible. If we start by making an empty aluminum box and then filling it with graphite, tiny air gaps will remain, especially near corners. After the graphite is crushed, the loosened carbon powder may shift into those spaces, changing the center of mass and contaminating the measurement. To avoid this, our approach is reversed. We first compress pure carbon powder into a dense graphite block, ensuring maximum internal uniformity. Only then do we wrap the block in aluminum plates from all 6 directions and apply pressure, locking it into a solid, sealed unit. This method minimizes internal gaps and guarantees a stable mass geometry, even after ultrasound-induced expansion. This type of 6-directional encapsulation and mechanical compression is already mature and widely used in materials science and battery module fabrication, where uniform density and structural integrity are critical. Why 6 mm aluminum walls matter? When we crush graphite with ultrasound, the combined effect of carbon powder expansion and ultrasonic vibration can push against the container walls. If the walls are too thin, they may deform slightly, shifting the center of mass by a few microns. That small shift could register as a false change in gravity. That's why we chose 6 mm thick aluminum walls. At this thickness, using 6061 T6 aluminum alloy, the deformation after ultrasonic shock is estimated to stay under 0.4 microns, which translates to less than 4 parts per million in gravitational noise. For context, the source-to-detector distance in most G experiments is around 20 centimeters. A 0.4 micrometers deformation would shift the center of mass distance by about 2 ppm, producing roughly a 4 ppm change in gravitational strength after the inverse square scaling, a predictable and acceptable effect well below the expected signal level. Even better, any residual noise can be averaged out with repeated trials. 6 mm aluminum strikes a good balance. Strong enough to hold shape, light enough to avoid dominating the total mass. It ensures that the geometric effects stay well below the signal we're trying to detect, the possible gravitational effect of increased entropy. Modern techniques still disagree with each other. Another reason for G6. Even with the most advanced technology of the 21st century, the problem remains. Since the year 2000, every new method, torsion balances, beam balances, cold atom interferometers, and resonance systems, has claimed unprecedented internal precision, some within plus or minus 14 ppm. Yet the measured values of G still diverge by more than 300 ppm across different methods. Let's take a few examples. In 2000, the University of Washington team, Gundlach and Merkowitz, achieved one of the most stable torsion balances ever built, reporting an uncertainty below 14 ppm. In 2014, the Pisa team, Rosie et al., used cold atom interferometry, a completely different approach, and obtained a G value roughly 200 ppm lower. Each of these results is self-consistent and highly precise, yet they don't agree with each other. Traditional explanations blame unmodeled systematics, vibrations, calibration, environmental drift. But such errors should appear random, not clustered in consistent offsets between methods. That's why we think the missing factor is structural, the internal information patterns of the materials and systems themselves. If each experiment's setup carries a unique distribution of entropy, then each effectively measures gravity in a slightly different information state of spacetime. This is why G6 matters. It's the first experiment explicitly designed to control information entropy as a variable, rather than treating it as noise. One more reason for G6. Existing explanations have reached their limits. For more than 2 decades, the global metrology community has systematically analyzed every possible source of bias in G measurements: air buoyancy, thermal gradients, magnetic coupling, fiber torsion, electronic feedback drift, and seismic vibration. Yet even after accounting for all of these, the spread between independent laboratories remains in the range of hundreds of parts per million. The persistence of such a structured, non-random deviation suggests that the missing variable may not be an instrumental artifact, but something deeper, perhaps rooted in the material itself, such as its internal information entropy. After G6. G8 and artificial gravity. When G6 shows that entropy truly affects gravity, then the next question is, can we control it? That's the vision behind G8, the next step in the series. While G6 focuses on detecting the link between information and gravity, G8 will explore how to generate or modulate gravity using controlled flows of entropy. In short, in G8 we put a sensitive detector near a cluster of supercomputers, which is the most powerful entropy source today. Check if the cluster produces fluctuating gravity based on its workload. We will further introduce this plan in future video. The G-series, a branch of the DST framework. The G-series experiments are part of a broader theoretical framework called DST, discrete sampling theory, a framework proposing that time itself is not continuous but made of discrete frames, subtly suggesting that the universe may behave like a simulation or computational system. The earlier designs, G1 through G5, either require unachievable precision or prohibitive cost. That's why G6 is the first experimentally actionable step in the whole DST, not only G-series. If G6 detects a gravity shift caused by entropy increase, it opens the path for future tests. G7 is the reverse of G6. Instead of increasing entropy by crushing graphite, G7 would reduce entropy, such as by freezing disordered water into a crystalline solid, and check if gravity becomes weaker. This is much harder. The final structure must be more ordered and still fill the container completely. Very few materials meet this condition. Also, entropy-decreasing processes are often anisotropic. For example, freezing usually starts from a specific surface. G8, previously proposed, involves using dense supercomputer arrays to test if regions of high algorithmic information density could influence local gravity, essentially probing the limits of artificial or synthetic gravity. G6 to G8. Skipping G7 by using a bidirectional entropy source. The G6 experiment is designed to test a one-way hypothesis. If entropy increases, e.g., turning solid graphite into disordered powder, does gravitational strength also increase? Traditionally, to confirm whether this entropy-gravity effect is symmetric, a follow-up experiment like G7 would be needed. One that starts from a high-entropy state and reverses it to a low-entropy state, like from water to ice, to see if gravity decreases accordingly. However, the reverse pathway poses major technical challenges. Entropy reduction, like crystallization, is often non-uniform and directionally biased. It's difficult to achieve large-scale entropy reduction without introducing secondary shifts in mass center or volume. To bypass these limitations, we propose a direct transition from G6 to G8, using a fundamentally different kind of entropy source. G8. Supercomputing arrays as dynamic entropy sources. G8 replaces passive material structures with an active system. A dense, high-powered supercomputing array acting as the gravitational source mass. Through software control, the system's internal information state can be modulated over time. Processing load and memory architecture shift dynamically. Instruction entropy increases and decreases as programs run and terminate. These fluctuations are fast, sub-second, measurable and repeatable. If a nearby gravimeter detects tiny real-time changes in gravitational pull that track the system's entropy state, it would strongly suggest entropy affects gravity in both directions, not just entropy increase but entropy reduction too. Why we still need G6, even if G8 covers both directions. While G8 is capable of testing both increasing and decreasing entropy, its experimental system, a supercomputing array, introduces many complex variables: electrical currents, heat output, electromagnetic fields, and internal structural vibrations. Even if G8 observes gravitational changes, skeptics could argue it might be the power fluctuations, air flows driven by the heat, or mechanical vibrations, just not the entropy. That's where G6 plays a critical role. G6 is a minimalist, tightly controlled setup. It holds mass, shape, material, and environment constant. It changes only one variable: the internal entropy of a sealed block of graphite. The entropy shift is induced without altering total energy or external forces. If G6 detects a change in gravitational strength under such isolated conditions, it provides direct causal evidence that entropy, and not heat, electricity, or vibration, can influence gravity. In essence, G6 isolates the variable. G8 explores the dynamic reaction. Without G6, G8's results could be dismissed as correlation. With G6, we prove causation, and together they close the loop on the entropy-gravity hypothesis. If G6 confirms entropy increases gravity, then the interaction must be bidirectional. If the G6 experiment confirms that increasing entropy leads to stronger gravity, then the conclusion isn't just one way. It implies a bidirectional coupling between entropy and gravitational strength. Here's why. In nature, entropy is always changing. Water freezes, ice melts, crystals grow, molecules break down. If entropy only increased gravity and never decreased it, then every local entropy increase would leave behind a permanent gravitational offset. Over time, gravity would accumulate. But that's not what we observe. For example, water freezes, entropy down, then melts again, entropy up. These processes happen millions of times a day on Earth. If each increase in entropy made gravity slightly stronger, and the reverse didn't reduce it, then over time ordinary materials like water would develop absurdly strong gravitational fields, even rivaling black holes. Since this doesn't happen, the only logical conclusion is, if entropy affects gravity, it must do so in both directions. This means that G6 is not just a test of yes or no. It becomes the gateway to a dynamic gravitational model where entropy and gravity are symmetrically coupled. And if this symmetry holds, then G7, a high-difficulty experiment designed to test entropy reduction, is no longer essential. G6 alone, supported by the logic of natural entropy cycles, would be sufficient to imply bidirectional gravitational response. Call to labs worldwide. Join the G6 experiment. The G6 experiment offers a rare opportunity, a testable minimalist design that could challenge the foundations of gravity theory at a fraction of the usual cost. For under $100,000, any well-equipped university or private lab can attempt to verify one of physics' most puzzling anomalies. This isn't just a precision test. G6 isolates a variable never directly measured in gravitational experiments before: internal entropy. If verified, the results could reshape our understanding of mass, structure, and space-time, and may well point toward a new coupling between gravity and information. We invite experimental physics teams around the world to replicate or expand on G6. The setup is simple. The implications are historic. And the recognition, if successful, may reach Nobel heights. Whether you're an academic lab, a national standards institute, or a private foundation pursuing fundamental science, this is the experiment that lets you make history without needing billion-dollar infrastructure. For full specs, data templates, and Q&A, refer to the essay with keyword G6 experiment in Zenodo or contact shykittyofficial@gmail.com.